We're going to be talking about rate laws today. Rate laws are very central to this chapter. This might be the most important thing that we cover. So a rate law describes how the rate of a reaction varies with reactant concentration. So if we write a generic reaction, like this one, A plus B plus C goes to products, then the rate law has the form rate equals K times A, concentration of A to the X power, concentration of B to the Y power, concentration of C to the Z power. We're going to talk more about this rate law now. So here's our generic expression. That's the rate of the reaction. Lowercase k is the rate constant. It's a constant for a given reaction at a given temperature. That's the initial concentration of reactant A. The brackets with B in it is the initial concentration of reactant B. And then C in brackets is the initial concentration of reactant C. That shouldn't be too shocking. What's new are these exponents, X, Y, and Z. These are called reaction orders. They are generally integers. They can be 0 or 1 or 2. Other numbers or fractions are far less common than 0, 1, or 2. X would be called the order with respect to A. Y is the order with respect to B. And of course, Z is the order with respect to C. If you take the sum of those three numbers, then that would be the overall order of the reaction. And as I mentioned, those values are usually 0, 1, or 2. Now these are some examples from your book of actual rate laws that have been measured, determined experimentally. So we're going to talk about each one of these just to make sure it's very clear. Start with the first one. This is an unusual designation. SOLN is one that you don't see a whole lot. It's kind of like aqueous. It's in solution, but it's when the solvent is not water. That's just a little sidebar. What I wanted to tell you is that we have 1 mole of this first reactant. We have 1 mole of water. And then when we compare that to the orders in the actual rate law, which is listed on the right, it is first order in the first reactant and 0 order in the second reactant. And you know it's 0 order because that reactant doesn't appear. The second reaction here, we have 1 mole of the first reactant. That's formic acid. We have 1 mole of molecular bromine. But our rate law does not mention formic acid at all. It is first order in bromine, and it is 0 order in formic acid. What that means is that the formic acid concentration has no effect on the rate law at all. So it's raised to the 0 power, and anything to the 0 power is a 1, so it doesn't appear in the rate law expression. First order with respect to bromine means that if we double the bromine concentration, the rate should double. We'll talk more about that. The third reaction here, we have bromate ion, 5 moles of bromine, 6 moles of hydrogen ion. But the stoichiometry of this reaction doesn't necessarily have anything to do with the rate law, because you can see the rate law is first order in bromate, right? There's a understood 1 exponent. It's first order in bromide ion, and it is second order in hydrogen. You can see the 2 up here, right? Second order in hydrogen. The overall order of this reaction would be 1 plus 1 plus 2, which would be 4, which would mean it would be fourth order overall. One mole of hydrogen reacts with 1 mole of iodine. In this case, the rate law does seem to match the stoichiometry because it is first order in both, and it's second order overall. So the take-home message from this table is that rate laws must be determined experimentally. They are not obvious from the reaction equation, from the stoichiometry of the reaction. We're going to talk more about why that is later. But for now, you just need to know that rate laws need to be determined in the lab, empirically or experimentally. On the left, you see different rate laws written in their generic form. So we have a 0 order rate law and a first order, and one that's first in A and first in B, which is second order overall. We have one that's third order overall. This is just showing you the units for K, which are on the far right column. Units for K can easily be determined during the calculation as well, and I will show you how to do that. But you could also memorize them. They are here in this table if you'd like to memorize them. Now I want to do a practice problem where we determine a rate law using the method of initial rates. And this is something that you definitely need to know. It will appear on your quiz, it'll appear on your test, it'll probably appear on your final exam, so you should definitely know how to do this. The following reaction was studied. We have 1 mole of NO reacting with 1 mole of oxygen to form 1 mole of NO2. We have data that tells us that 4 different experiments were carried out with different initial concentrations of each reactant, and the corresponding rate of reaction that was measured for each of those experiments. Then we're going to determine the rate law. This method for determining rate laws is called the method of initial rates. Put the problem back up. So what you need to do is you need to identify 2 experiments where one of the reactant concentrations is varied, but the other one is not. So let's see, if we compare experiments 1 and 2, it appears that the NO concentration is doubled, but the oxygen concentration stays the same. Comparison of 1 versus 2 would allow us to determine the effect of this doubling without having this concentration play a factor. That way we only have one variable and we can more easily determine the effect of that change. Oops, it looks like I didn't have a balanced chemical reaction up there. I changed that, added some stoichiometry. I think I got it right now, maybe. So we're going to determine the rate law. And we know that the rate law is going to have this form. Our goal is to determine what x and y are. So is it a 0, is it a 1, is it a 2? So we're going to start by comparing experiments 1 and 2, where NO doubles, but oxygen does not change. It's important that we pick one where oxygen doesn't change. This is doubled, and we're going to compare the effect on the rate. So if we then compare the rate of reaction and how that changes, we need to figure out what that factor is. Is that double? If you're not sure, you can make them a quotient. 0.192 divided by 0.048 is a 4. 4 means that this is second order in nitric oxide. And the reason that's true is because we doubled the concentration of NO, and 2 squared is a 4. So second order is this exponent up here. That's why it's called second order. It's because whatever we do to the concentration, the effect it has on the rate is whatever that change is squared. So it's an exponential relationship. So that 2 is because NO was doubled. And the other 2, it means it's second order. Okay, so the exponent is the order. Okay, it's kind of confusing because there's both 2's. But let's say instead of doubling NO, we tripled it. If we had tripled NO, then the rate would have changed by 3 squared, which is 9, right? Now let's figure out the order with respect to oxygen. If we compare experiments 1 and 3, it seems that NO does not change, but oxygen is doubled. The effect that that has on the rate, it's pretty obvious this time that that is doubled, but if you're not sure, you can again do the ratio. Therefore, you can say that this is first order with respect to oxygen, because 2 is the same thing as 2 to the first power. So that 1 means it's first order. That's the order. Remember, the order is the exponent in the rate law expression. It'll be 0, 1, or 2. So now we're going to write the rate law. It always has this form. Don't forget that you have to write rate equals. You need the lowercase k, and you need the concentration of whatever the first reactant is, NO, squared, because it's second order, and O2 to the first power. You can leave off the 1. And that's the end of our show.